Okay. Hello, everyone, and welcome to our second lecture in the ongoing double operatic theory of systems lecture series. We're not yet to double operads, we're still on categories. So let me review a bit of what we did last time, and this time we're just going to see, I believe, more categories of systems and more notions, more features of systems that are representable by maps between systems. So last time we saw two categories of systems. So last time we saw, we saw discrete time, discrete space, dynamical systems. Wow. That's a long phrase for just a single function u from S to S in the category of sets. Where a map here, so a map, and a map here is a function f from S1 to S2 such that the square commutes. So S1, U, S1, S2, U1, U2, S2, F commutes, i.e., for all S in S1, we have that F of U1 S equals U2 F of S. Okay, and we saw how sequences of states that update according to this law were given by maps out of the natural numbers ticking forward. So we have here we have a clock, which is n, and then we add 1 to n, and maps, so I'll call this clock, maps from the clock to S are sequences in S such that S m plus 1 is equal to U of Sn. So they update according to this. And therefore, they're determined by, therefore they're determined by S0. Okay, so I will call, like, one thing we could call this is, we could call this category set to the loop, because we think of this as it could be thought of as the category of functors from the category freely generated by a single loop into set. And so if we wanted to, we didn't talk about it last time, but if we wanted to have other kinds of discrete time things, we could look at other categories. So we could replace, for example, set to the loop. So this is discrete space, and this is all discrete time. But then we could also, if we wanted continuous space, right, we could use topological spaces and look at a loop. And that's the same, it has the same sort of category here, but instead of sets, it would be, so instead of this one here, instead of sets, it would be topological spaces. And then this map would have to be continuous. And it's perhaps much more common to see also measurable spaces. So this would be continuous space, continuous dynamics. And this one here is measurable space, measurable dynamics, which is the most common one you'll see in practice. But we can also do in other categories. And so I think I'll try and get to other interesting categories, like say, we'll see some other interesting interesting categories here in discrete time, like partial maps, which gives us non-determinism. And Markov kernels, which gives us stochasticity. So I'll try and come to those later today. So we also saw continuous time. You saw continuous time in the form of ODEs, ODEs, and we saw that ODEs can be represented as vector fields. So ODEs as vector fields. So an ODE is an ordinary differential equation. Okay. So a vector field is we have some kind of manifold S, which you could think of as being Rn, and we have its tangent bundle Ts. And the tangent bundle is, roughly speaking, pairs of a point S and S paired with the tangent space at that point, like this, and these are the sort of infinitesimal changes to S. They're the infinitesimal changes you can make in the state. And so a section here, U, is a vector field. So this such that pi U equals id S. In other words, we have U of S is in TSS. In other words, in this time, instead of saying what the next state will be, we say in our dynamics, we say how to make an infinitesimal change in the current state. And a solution of U is an actual function of time. So in fact, I might write it I might bind a variable in R just to tell you this is a function of time. Right? So it's a function of time such that the derivative of S with respect to time is equal to U of S of T. R. And then we also saw that this as well can be expressed as a map of ODEs, where this is the constant one vector field. So the unit time, this sort of represents the ODE dt equals 1. And then here is S, and here's S. Here is TS. Then this is T of little s. And that is the push forward of vectors. Which is given by taking the directional derivative. Or just a derivative in this case, because the domain is R, so there's one direction. And what we need to commute is these the bottom the sort of squares that go down, the square that goes downward always commutes, and what we need to commute is the other one, i.e., we want TS of 1 to equal U of S, and TS of 1 is precisely the push forward. So this is actually just ds dt, and there we have our from up top. Okay, so I want to talk about a few more kinds of systems today. I also want to talk about a few more kinds of representations. So let's see some more representable notions of the systems we've already had. So one is steady states. So let's do the discrete time. Right, so S in S is steady for U when U of S equals S. Very nice. So now, as we mentioned last time, you can represent elements of sets by maps from a single element set. So this is a map from a single element set with a single dummy element to S. Right? It just picks out that, it sends that dummy element to the element we need. So I'm gonna always identify elements with maps from this terminal set. And so, right, that's just what that means. So in other words, we have here a map like this. We have U, and then you can see that this equation expresses a sort of commutivity. If I put here another copy of S, and here I put the identity, which is the only map that I could put there, that this equation here becomes this commutative square, and this is a map from this thing here as a single object to U as a dynamical system. So in other words, steady states are representable by, well, what is this system here that represents steady states? Well, it is, in a sense, the system that only has exactly one steady state, because you see it has a single state, namely star, and that state updates to itself. So this is, by the, if we will, steady state. And it's just like how trajectories are representable by the trajectory, the system that just has a single trajectory updating, which is sort of a clock. So we saw that maybe I should say here, this thing here, which expresses the ODE dt equals 1, acts as our sort of clock for ODEs. Okay. So, excuse me. Okay, and also, so that's in discrete time. But in continuous time, we can also do that. So S as a steady state is steady for U, but now U is a section of the tangent bundle when, well, US is now not the next state, it's how the state is changing. So if we want the state not to change, we need it to be 0. 0 is the tangent vector that says you don't change, right? And that again is also representable, because here we can put T star and star here to S. Now I'll note that this is a manifold. It is R0, right? It's R to the 0. It's we might call that element the single point 0 if we want instead of star. Here. Here's S, right? And here is U. This is, and here, right? Well, we're going to put this here. The tangent bundle of R0 is also R0. So this is in fact going to be, roughly speaking, the identity, because this is isomorphic to just star again, or maybe I should say 0 here. Because of that, this picks out a single element, and it's the derivative of this function, S. That function is constant. It can't vary. It has no domain over which to vary. So this is actually picking out 0. And so again, we see that this commutation here expresses this equation. So steady states are representable by, again, the steady state. It's a system with exactly one state, and its dynamics. This thing represents the equation d d, or if it will, d. There's no variable here, so it's a dx dt or dt equals 0, but also so t equals 0. I don't know exactly how to say this. There's only one state in here; it can't change. Okay. So steady states. Another thing we can talk about are periodic orbits. Right? So in discrete time, we might have a state here. So S in S is periodic when, for U, when U to the n of S is equal to S for some n, some period n. So in other words, it's a state is periodic when it eventually comes back to itself, but it doesn't have to do so on the next step. Usually the period is defined to be the smallest such n. And again, this is representable, where now we're going to take the set. So now, right, we actually have quite a, this equation here refers to something that's a little bit further in time, right? So there's sort of a bunch of intermediate values that aren't mentioned here, which is to say there is S, there's U of S, there's U squared of S, there's U cubed of S, all the way to UN of S, and that's the one that equals S. So in fact, these many things, right, of which there are n, these many things we need to sort of name in our representer. And so our representer here will be 0, 1, 2, ... n minus 1, which is often referred to as brackets n. And as we see, this sequence here, I'll just call S. Well, if I define or like wait, I guess I should say it's U blank of S, like that, to S, and then here is U, and then we need this again. So here's brackets n. Just make it, it's the same set. And then here we're going to take U blank of S. And now we want to put something here so that this commutativity expresses that. And what we'll do is plus 1, but now we need something special because it's certainly true that in this sequence, right, Ui of S, U of Ui of S is Ui plus 1 of S. That's by definition, so that's perfectly fine. But then when we get to UN, we want that UN of S to equal U0 of S, which is just S. And so we're just take it mod n. So there you go, shifting up mod n. Okay. And so that gives us, so in other words, periodic orbits also representable. Also representable. And if you note, this thing again is just the periodic, or this is it has a single state 0, which is periodic, because if I hit with plus 1 mod n times, I get back to 0, and no less. So this is a true period, and that's the smallest n for which it is. Then this is the system that just has a periodic point. Right? And what's kind of fun is by looking at sort of quotients of systems, so maps of systems that are surjective here, we can see that we're going to get the sort of divisible, the parts of the smaller part periods that we could get here. And so there's a sense in which like nothing about this said that n was minimal. Nothing about having a map like this said that n was minimal. But if we sort of take the image, it will factor through something that will be minimal. We can also do continuous time. So S is periodic. Well, now S has to be a time varying function of states, is periodic when S of t plus n is equal to S of t for all t. Right? And so you can see that it has to be a trajectory. This should say solution of ds equal us. It has to be a solution, which, as we saw, was already representable. But now, just as here, we took n modded out by n, or, if we will, plus n. Here we can take r modded out by plus n, and that's equal to the circle, or isomorphic to a circle. And so how does that work? Well, the actual quotient function there is usually given by an exponential if we wanted it to put it in the circle in the actual plane. But we can arrange this well enough. So if you if you have a map from the circle here, which by the way is I'll say 1, but it's the radius, if you will, the radius sort of depends on n, in a way that I haven't prepped for, and we'll make a mistake. And undo pi. The relationship between n and the radius will depend on pi and n. Right. So if a circle goes to S, right? This is the function S. Now it looks like it's a function of 2 variables, but we want to think of it as also we could think of it instead as a function of the angle. So we could think of it as a function of the angle, cosine theta, sine theta, for theta and r. And thinking about it that way, now we see that it's really they can be expressed as a function of 1 variable, and that's the one we're doing. And I'm definitely going to mess up the actual relationship between this and n, but n doesn't even have to be in this case, doesn't have to be a natural number. It could be a real number. Okay. And the actual tangent vector here, if you think of the circle like this, the tangent vector is going to be the one that you would get like this, sort of the canonical flow. I'm going to add a few more. It's the canonical flow around the circle. Okay. Okay, so we've seen a number of different little quantities that are representable by maps into dynamical systems. Now let's talk a little bit more about other kinds of dynamical systems, and other sorts of representable things we can do with them. So, okay, so more systems. So 1, labeled transition systems. These are labeled transition systems. This is an attitude towards labeled graphs. So by a graph, I'll always mean a category theorist graph. So a graph is a directed multigraph. So it has a set of edges, EG, and a set of nodes, NG, and then 2 functions like this, which we'll call source and target. And so this is the set of edges. This is the set of nodes. And every edge here, E, goes from SE to TE, like that. And so just as an example of this, if we wanted to write the graph here that was like A, B, C, and it had an edge there, an edge there, and a loop here, because I can have a loop, and it's allowed to have an edge going back. So now I have to label all these 1, 2, 3, 4 right? Then down here for ng is going to equal the set A, B, C. EG is going to equal the set 1, 2, 3, 4. And the maps that go down are going to express the relationship. So for example, 1 is going to go to A under S, and it's under T, and it's going to go to B under S. And similarly for all the other relations there. Okay. So now a graph homomorphism is a natural transformation formation of this data. And what that means is phi from G to H consists of maps of both the underlying datas here. We would call this E phi, or maybe phi E. Phi N. And then so that both the squares commute here. T, both those squares commute. And so what does that mean? I.e., we have, if we have an edge E from A to B in G, we get a map from phi N A to phi N B phi E E. And I usually am going to suppress the subscripts and just write all of these things as phi. So a map of graphs preserves source and target. Okay, so now an example, so an edge labeling. So an edge labeling thing of a graph G is a function e.g. L to some set of labels. We usually pick the labels in advance, so I would say in L. Okay, so we can actually express this. So equivalently, an edge labeling is a homomorphism from G, I'll also call it L, to this graph called BL, where BL is equal to L as edges and a single node, which we call star, here. And well, there's only one function you can take from any set into that set with a single element. You got to send everything to that single element. So in other words, this is the graph here which has one object star, and all the elements of L are considered as loops. So if you think of that homomorphism, geometrically speaking, sort of, it takes all the points of G and it crushes it into a single point. You're left with a bunch of loops, and you map those into each of these labels, right? So now, with that point of view, it's quite nice because now we can say, so a map of labeled graphs is a commuting triangle or commuting square, let's say, G to H, BL, like this, where this is LG and this is LH, this is phi. In other words, a map is simply, so if we write this out, the labeling LH of phi of E is equal to LG of E. In other words, a homomorphism of labeled graphs is a graph that is a graph homomorphism that preserves the labelings. Cool. So now that's a bunch of stuff like that. So what's a labeled transition system? A labeled transition system for a labeling set set L is a graph labeled an L. So we think of the labels here as actions. So this is equal to a set of actions. And the idea is that the nodes of the graph. So if we have, for example, G to BL, LG. So the nodes of the graph G are thought of as states, and the edges are thought of as these transitions, ways that you can change between states, and they're labeled by the action you would have to take to do that transition. So thought of as dynamical systems, these are discrete time, non-deterministic systems, because there's nothing here that says that there's a unique edge out with a given label. Okay, so now with that idea, what is sort of a behavior of these, sometimes known as a trace of these LTSs? Well, it's going to be a sequence. So given a sequence of labels, or given a sequence of actions, so given a sequence A1 ... AN of actions in L, right? We can define a trace for this sequence is a sequence of edges let's say E1 ... EN such that, you know, when we took the action, it had that, you know, they have the correct label. So we're taking that action on the edge and we have that correct label. And they have to line up. So these and they line up, which means that the target of EI is equal to the source of EI plus 1. So in other words, we have some kind of graph here, like A, B, C, or so X dot Y, maybe some other dots here. So, by the way, sometimes labeled transition systems are called flowcharts, which is a much nicer name for them. But and here is so I'll call this like 1, 1, 2, 1, 1, 2, 1, 1, 1, 2. And so for this example, L is equal to just 1, 2. And so you can see if I take my sequence here to be 1, 1, 1, 1, 1, 1, 1, 2, let's say. That will give me then a possible edge set for that sequence would be 1, 1, 1, 2, like that. So that would be a trace. But if I take it to be instead, if I did go back. If instead I did 2, 1, 1, 2, 2, 1, 1, 2, then I actually have multiple different traces for this. So I have to take this 2, but then I could have multiple different traces. I could go this way and then this way and then this way, or I could go, you know, this way, this way, this way, and then this way. And so as you can see, the behaviors here are sort of non-deterministic, but these are examples of traces. So maybe you can see what is going to represent this. If I put here N, by which I mean the graph now, which looks like this. . that. And I label it using A. In other words, I label the edge AI with the action AI, right? Then a morphism like this, here to here, well, it's going to send each one of these edges up top to an edge in G, and they have to end up, because morphisms preserve source and target, they have to line up. So as you can see, the traces of one of these labeled transition systems are representable in these ways. And these can be used for lots of different things, but often you might want to say that you have a source node and a sink node, and these have to start there. And if you added that data, you can still have this represent in that way by, say, marking certain data here. So one of the general ideas of category theory, let me maybe say that how that works. Let's say I wanted to do a source and target here. I'm gonna move this whole thing down. Let's say I wanted to also mark a source and target. Well, that's extra data that I have to put. So I should put that in my definition of system. So if I had a source and target node, right, like source target, I could represent that as a homomorphism into my graph G from the graph that just has two distinct nodes, source and target, right? But now you see that my diagram's looking a little awkward because I really should take my morphisms to be natural transformations of the data of each object. So I really should put some kind of source and target here, which is clearly going to be 0 and n. Right? And now I need it to be a natural transformation, so I need this to work here. These are actually going to be the same here. So maybe I should say that this is these are equal. This is source. This is target, and this is source maps to 0, and target maps to n. Right? Or source and sink is perhaps what I should say. Now, when this commutes, this also says that, in fact, the have to go, so maybe this is x and y here in our graph over on the right. Now, for that top square to commute means that 0 has to go to x and y has to go to and n has to go to y, because those are the source and sink of G. And so you can see the general idea of in category theory is sort of you derive the notion of the correct notion of morphism from the definition of your objects. And if you want to add extra data into your notion of system, you should keep track of it in your notion of morphism. But when you do, you find that if your notion of behavior required understanding that extra data, like a source and sink, right? So now you only want traces to go from source to sink, then it will still appear in the map. The extra conditions you need will appear in these sort of maps between them. That's sort of a takeaway. Okay. So we have labeled transition systems. At some point, these lectures are going to start rapidly increasing in categorical sophistication, but I think we're going to stave it up for one more. And I'm going to talk about non-deterministic. So let's talk about now discrete time non-deterministic systems. So the simplest kind, the simplest kind of non-determinism is where we don't know exactly what the next state will be, but we know a set. So is non-determinism of non-determinism is going to be possibilism. So we say from U, it takes a state not to a next state, as in determinism, but it takes it to a set of states. So this here is the power set, i.e. set of subsets. So now, right? Now that's a reasonable notion of system, and a morphism here would be something like this: S to PS Well, maybe I'll leave it off and we'll do other. The notion of morphism here is a little like doesn't follow the scheme exactly, in my opinion. So we'll come back to it in a bit. The next is stochastic. And here, what we want to say is that U of S, so U of S here is a subset of S. This one, right away. So U of S now we want is a probability distribution. It's a conditional probability distribution on states. So U of S, normally this would be written P given S, where P stands for probability, but really you have to actually say what distribution you're drawing that probability from. So that should be said somewhere. And so we would say as U of S could be this, but we should say U of S is a probability distribution that looks like this on S. So we can think of U now as a function to the set of probability distributions. It's often denoted as delta. And this is the set of probability distributions. And I will note that so right now we have both of these have a similar form, or I might do a few other ones. There's also just like potential to halting. So this is non-deterministic in the sort of simple sense that it is deterministic, really, but a state might go on or it might stop. So we might say that here we have U, S goes to S, disjoint union, bot, where here we call this the halting state. Halting. And it's not, instead of considering the halting state to be a separate state of its own, we are going to consider it to be an extra state that sort of gets added on at the end. The reason is that the halting state is supposed to be where your system just stops, so there's no reason to define a dynamics for it. If you want, you can always extend this to a function that just U sends bot to bot, but I think keeping it this way shows that there's sort of this pattern here, thing here. This is sometimes known as maybe S in the computer science literature, by definition. In other words, U here is a function that takes in a state and will give us, well, it will maybe give us a next state, or it will halt. Right? And so in general, we have a monad. Well, I guess it really doesn't need to be a monad. I'll just say an endofunct, a functor F. I don't know why my F got so fancy. I have to save my fancy letters for a serious climb up the category dimension ladder. That's going to happen. From set to set. And so this functor, like that sort of describes our non-determinism. Okay, I'll do it this way. Right? So we have S to F of S, U, is an F non-deterministic system. So we have in case one, we had F equal power set. In case two, we had F equals delta probability distributions. In three, we had it being the maybe monad, as it's called. Maybe we add an extra thing, but there's so many other things we could do. We could we'll see a number we'll see more of these as we talk about systems that can actually couple with each other, which we're gonna, I think, at this rate, come to next time. And of course, we don't actually have to be from set to set. We could be from any category to any category, because of course, this formulation here works in any category in Z. So the obvious notion of morphism, as a category theorist would say, is going to be like this. Oh, and I should say this, 0 here is f equals the identity functor is determinism. If f is the identity functor, which is to say it just takes s to s, then it just sort of disappears in all these formulas and we get back to where we were. Okay. So this here says a number of things in all these cases, but we have to understand how a functor acts on these morphisms, right? So in this case, right, in this top one here, a homomorphism, maybe I'll do homs. In one here, a hom would be something where, as you can see, it would say that you have to understand how the power set is functorial, and it's going to be functorial by taking the direct image, right? So this would say that sorry, where's my eraser? Here. That U2 of f of s is equal to f, maybe I'll put lower star and say that it's a direct image of U1 of s. That's actually a rather strong condition. It's a rather strong condition because what that says is that, for example, if we tried to do our trick about representing trajectories, this would have to say that actually, if we tried to do, for example, in this case, right, it would be U2 of say n plus 1 in our plus 1 trick. Here would be, well, it would be the U1 is, sorry, U1 of n. That's right. If we tried to do this where S1 here, down here was maybe like N2, and plus 1. A lot of these functors, all of these functors have a case of Dirac delta or singleton inclusion, or unit, as it's often called, that would let us promote a system into the other kind. So this would be S1 here, Sn. And the other kind here, well, U1 of Sn is Sn plus 1, and then we have this F lower star here. So it's just F. Well, now it's just really a singleton at F of Sn plus 1. And that is rather strong. That says that actually the sequence, so the clock for non-deterministics with this kind of morphism only gives you behaviors that do update deterministically. So you're losing a lot, right? For the stochastic one, it turns out that you can actually get the correct notion of behaviors updating according to law, where now we take the push forward of distributions, which is given by sort of the so maybe I don't know how much I want to go into this, but the actual formula for the inverse image, right, is the set of all, or maybe I'll do it, yeah. It's the set of all S2 such that there exists an S1 in U1S and F of S1 equals S2. And the push forward of distributions is equal to the integral over all S1 such that f of S1 equals S2, valued at S2, of the U of the probability. Oh man. I can't do this off the top of my head. I'm sorry. The danger of not prepping any of these lectures. Um, maybe we could pause and I could look it up. Right. We're doing here things over set, so I'm going to avoid any measure stuff. It's in fact a little easier to write the formula with the measures involved, but be F inverse, so it will be S. We have to know what pushing forward a distribution even looks like. So sorry. We're going to define we're defining these on sets so we can define them on their elements rather than on some element here in S2. S2 of U1 S. So this is the sum over the inverse image of the value of the thing. And this is very similar to this exists over the inverse image of of the truth of a predicate. So that is where that happens. And here, f star u1 of s is just equal to, well, there's two cases, f of s or bot, depending on whether or not u1 of s was bot or not. Okay, so in this case, what we see in this case, again, the notion of transformation down here would be very strong. Um, but it turns out that you can actually get a good notion of representable behavior. But I'm going to have to leave that for another lecture, and which I will cover because I think it's quite cool. Um, uh, and you can't quite do it over the category of sets so well. It's really a point where you have to start to use measure theory and really do probability theory. But in the maybe case, what you see is that it does say that if you halting states have to go to halting states, and that's not terrible. Right. But in general, this is not necessarily the right notion of morphism. It's actually very this actually does have a really this formalism does have a really good use case for understanding um, uh, systems with interfaces, which we'll probably come to. But right now, I'm going to say that these are known as co-algebras for F. And maybe I should leave it there. And we've seen more kinds of systems. We've seen a bit more kind of representability. We've seen where the sort of quote unquote obvious. Oh well, I'm going to do one more. I'm going to do one more thing. We've seen where the obvious notion of map of system is not necessarily the right notion with respect to representability. But let's also see how we could change that to get a very perfectly reasonable notion of map, very categorical feeling, right? But nevertheless upgrades our representability. So now let's talk about like trajectories of discrete time possibilistic systems. So again, a possibilistic system sends every state to a set of future states. And so we'll say a trajectory here is a sequence Sn, you know, so that, well, what we don't want to say that just Sn plus one equals the other one because the other one's a set and this is a single element. That was sort of a problem. But we want to say that it's a possible updated value in. And then I will just immediately reformulate this by saying that Sn plus one, the singleton containing Sn plus one, is contained in U of Sn. So now let's go back to our formulation here. We had Sn, we have +1. Well, I'll put it around singleton +1 to Pn here. Pn. In other words, I here, or n, maps to the singleton set containing n plus 1. And then we'll have our sequence S here. We'll have our non-deterministic update here. And here we're going to have our P of S. And so if we look at where this part goes here, it's going to go to the image of the singleton here. So this one is the singleton at Sn plus 1. Meanwhile, this n here goes to Sn. And here we get the set, USN. So again, this square is telling us the right things, but we don't want them to be equal. We wanted a containment. So we want the containment to go this way. And this is what's known as a Colax map of systems. Taking a term from higher category theory. Because here what we had to use is that the power set is not just a set anymore. It's actually an ordered set. It has this ordering of subsets. And if we keep in track of that, there's an actual perfectly natural sort of notion here. So the general setting for here is Colax maps of co-algebras of endofunctors on a 2 category. I'm not going to go into that, but my point is that if you just try a little bit harder, you can often find that the right notion of map is just around the corner. And we'll come back to this later and talk about how this notion of map allows us to represent not just trajectories of non-deterministic systems, but also things like Lyapunov functions.